that is, I have to divide out a 2 and put in a 3. So that's 3/2 or 1.5. So if you go from there, that's not going to be an octave anymore. And this is not going to be an octave anymore. So I have to divide out a 3 and put in a 4. So whatever 4/3 is. So if I play for you this harmonic series, the first one doubles, but then they don't double anymore. So right? So they start to have decreasing spacing, because our ear, in a certain sense, here is multiplication, not addition. Okay. So that's standing waves on a string. And you might ask, can you do this with? So that explains how any stringed instrument works. You might ask, can you make standing waves and other things? Yes, you can. You can do it with sound. So let me show you some of those. Same idea. Almost there. Okay. So I don't know if that warning message will just go away. I could show you. At least I can show you the top. Okay, there we go. So let me show you first. Here would be a musical instrument with both ends closed. It's kind of similar to a wave on a string. It's got both ends that can't move, right, because they're tied down. So here is the actual oscillation of the air particles. That's actually physically what the molecules are doing. Remember, we're dealing with longitudinal waves now. So the motion of the waves left and right, the molecules are moving on the same axis. And we can draw in the displacement of the particles, or we can draw in how much the pressure differs from average pressure, which is, of course, just a fancy word for gauge pressure. Okay? So at the ends here, of course, the molecules can't move through that wall, so they cannot move, right? The displacement is 0. So that makes displacement nodes on the two ends. Okay? So in the middle, they can move. So that's where we have a displacement antinode. Okay? Now, I mentioned last time that there are two complementary pictures of wave amplitude for sound. One, you can talk about the physical motion of the particles, and one you can talk about the pressure. And I said that they do not co-occur, and I don't need you to know much about it except for this, which is what I'm talking about. The fact that they do not co-occur, it actually means that when you have a displacement node, you have a pressure antinode. Let me explain why when you have the particles can't move, it's a displacement node, it's a pressure antinode. I like to imagine right here that instead of air molecules, this is you at some big stadium rock concert, okay? Well, hopefully that's not where you're standing. Don't ever stand against the barrier at a big concert, okay? And the reason why is if you can't move, you have against the barrier and you can't move, you're going to be subjected to the biggest crushing as the crowd moves toward you, right? Because you can't move, a lot of pressure change. You should be somewhere in the middle, not touching any kind of hard barrier, because then if the crowd moves, you just go with it, right? So if you can move, if you can displace yourself, if you're a displacement antinode, you'll be a pressure node, okay? So just remember that, pressure nodes and displacement antinodes, just vice versa. And I'd like to point out that regardless of how you cut this, this is half a wavelength, right? So exact same thing we did before, right? This is half a wavelength. Half a wavelength here, half a wavelength here. We can go to the next harmonic. It looks like this. This is the n equals, whoops, did I go one too far? Yeah, there we go. So this is the next one. Looks just the same, right? Here's one full wavelength. Could do one more. Okay, all the same stuff. Let's go ahead and go with both sides open. What does that look like? It looks like this. Now because both ends are open, the particles are free to move on the ends, right? They're displacement nodes. They can move however they want to. And because they can move however they want to, the pressure stays at PATM on both ends, which of course we know it's open to the air, right? So how much of a wavelength is that? It's still half a wavelength, right? Still, next one, n equals 2 harmonic, we have a full wavelength. It's all the same stuff. So really the equation we came up with is when the ends are the same. The ends are like. They can both be nodes, they can both be antinodes. The only thing that is that they have to be like ends, okay? So this equation we came up with is really the like ends equation. They can both ends can be nodes, both ends can be antinodes. And in the case of sound waves, it's a good thing because whether both ends are antinodes or both ends are nodes just is which picture are you in, right? If both ends are antinodes of one, they'll be nodes of the other, okay? So that equation which we talked about is the like ends equation, all right? I'll show you another musical instrument, okay? This tube, it's open on both ends, and I can get the harmonics going in this too. So just like I did over here, n equals 1, 2, 3, 4. Try to get them in this. Same notes, right? Okay. But this is tuned a little different than that. I usually can get them to sync up. Let's see. Yeah. Yeah, same notes. So. Yeah, those are pretty close, okay? So, if you want to apply this to any musical instrument that makes a sound wave in air, saxophone, trumpet, trombone, didgeridoo, whatever you want, okay? What is this thing? This is called a physics tube. I have no idea. This is not an instrument that you would want to necessarily play, okay? What's that? It's just a tube.
It's just a tube.
Yeah, that's it.
Solid tube.
Yeah, that's right. For V, of course, it's a sound wave. So in air, just use 343 meters per second, and you're done. You don't have control over that. You can't control that anymore like you can the guitar string, right? So you can't mess around with V if it's a standing wave in air. You can change L. So all of your instruments have some mechanism to control the effective length of air that's able to resonate. So the keys on a saxophone or trumpet or whatever basically control that. If you don't have that control, then you are kind of out of options except for N, right? So that's the only thing I can control here. I can't control V because it's sound wave in air. I can't control L because L is what L. So I can get the harmonics, and that's kind of it, right? Now you might say, well, this instrument is silly. Who would want to play this instrument with these 3 or 4 notes that it can play? There is such an instrument. It's called a bugle. A bugle is a trumpet with no keys. Why would you want a trumpet with no keys? Well, I guess, I don't know, they gunk up on the battlefield, so you don't want to have keys to mess with. I'm not going to try to play it with the tube, but I can approximate them on a guitar by giving myself the restriction that I can only play harmonics. You may have heard of some songs that have been played on a bugle. There's the, I can't play it. That's the Charge, Let's Go Get 'Em song. I don't know what that's, there's a name for that. And then there's the, I think it's called Taps. Taps is the one where everyone's going to bed, right? harmonics, right? It's the same 3 or 4 notes. That's all you can play on a bugle is 3 or 4 notes. You just have to invent songs that aren't boring with it, I guess. Okay. All musical instruments, even something like drums, you're basically just creating standing waves on a membrane. Like a snare drum or something like that, the node is on the outside because that's where the skin is held down, and you hit the middle, and the middle becomes the antinode. Okay. So lots of all musical instruments based on this idea in some way. And if you think that it doesn't have application outside of that, well, we don't cover drums because that's complicated because it's in 2 dimensions. You can even have standing waves in 3 dimensions. Okay. Let me give you an example. The n equals 2 harmonic, that one, that sure looks a lot like a p orbital. Okay. So electrons as waves are just standing waves in 3 dimensions vibrating around the nucleus. Okay. So the one case that we need to talk about is what if happens when the ends are not the same. So what if you have one end that has a node and one that's an antinode? So for that, we'll just go through the same kind of strategy and figure out what comes out. So let me show you what you get. So this is the first one. That right there is a quarter of a wavelength, right? So the first one, that's a quarter of a wavelength. In the length of tube, that's 1/4 of a wavelength. That's the longest wavelength that can fit in, where one end's a node and one end's an antinode, right? Let me bump up to the next one. The next thing I can fit in that makes sure that one end's a node and one end's an antinode is like that. That is a 3/4 of a wavelength, right? So I can fit 3/4 of a wavelength in there. Let's check out the next one. That's the next thing I can fit in there that obeys the boundary conditions, one end being node, one end being antinode. That is a wavelength and an extra quarter. One full wavelength plus an extra quarter, that's 5/4. So the pattern seems to be that I have to up it by an odd number of quarter wavelengths. Okay? So the pattern is this. If I wanted to make a general formula that encompassed that, I'm talking quarter wavelengths. In this type of system, n is the number of quarter wavelengths. Why quarter wavelengths? Well, if you add in a quarter wavelength, it allows you to go from a node to an antinode. And why only odd ones? Well, the problem is that 2 quarter wavelengths make a half a wavelength. And why don't we want half wavelengths? Because a half wavelength will just allow you to not get in the extra. So if we had an antinode on the end there, we want to get another antinode on the other side, right? So we want to progressively add how do I put this? If I had this one, if I had a quarter of a wavelength, right? And now I have an antinode in the end. If I added 2/4 of a wavelength, I'd have a node on the end now. Okay, so I don't want that. So it's just odd numbers of quarter wavelengths. Okay, so that's the pattern. And in this kind of situation where you have unlike ends, there are only odd harmonics. Even harmonics do not exist. So if someone asks you for the second highest harmonic, you put in n equals 3, not n equals 2. So taking this equation and similarly solving it like we did the last one, you get this. This is the unlike n's equation. Anytime the n's are different, you use that. So there are two equations to use. One for like n's and one for unlike n's. Okay? So let me show you something in comparison. Let me compare a flute to a clarinet. So why do the flute and clarinet sound pretty different? Well, one reason why an instrument could sound very different is L, right? If L is larger, the frequency is smaller, right? That's why all the instruments that are very tiny play very high, right? Piccolo and stuff like that. And then the instruments that play low notes get very big. So didgeridoo, tuba, where you literally, it's so long you have to wind the tuba around like this, okay? But that can't be the answer for a flute and a clarinet, because a flute and a clarinet are basically the same size. You're not comparing a piccolo to a tuba. The lengths are the same. And if we're talking the lowest note that they can produce, let's make it a fair comparison. Let's go to n equals 1. Well, and of course V is the same because they're both sound waves, so what's left? Well, it turns out for a flute, you can, the way that it's constructed, it's got like ends. Whereas a clarinet, the way it's constructed, they have unlike ends. So for the flute, it would be appropriate to use our first formula, NV over 2L. And over here, it would be appropriate to use NV over 4L. So the factor of the numerical factor in the denominator, one's a 2 and one's a 4. Well, what does that mean? It means that this tends to be twice this one, which we know is an octave. So a flute plays about an octave above a clarinet. A flute plays a much higher note. And the reason why is simply the construction of it, such that the flute has like ends and the clarinet does not. I can try to demonstrate this for you. I have a slide whistle. So, if I can get it out of here. So a slide whistle, this is something where first you can vary the length, right? If you make it longer, it'll be shorter. Frequency will go down, right? If you make it shorter, it'll go up. Okay. I can also experiment with the ends being like and unlike. Okay. So this right here, even though I'm blowing into it, and there's this gap here where you can see that it's open to the air, and then this is also open to the air. So I play it like that. Actually, sorry, I think this ends up being the unlike ends because this does taper significantly, so it's still mostly closed. So let's see. Yeah, so basically this is when the ends are like. They're both stopped up, and it plays higher, and then here, when the ends are unlike, it plays lower. And if you know music, you can hear it's about an octave. Right? Okay. So that is it. I think that I'm not. Oh, and there's one more thing I can show you that's very, very brief. Can I? Let's see. So, you know what? Let's just call it a day there. I'm going to have to chop a couple things from the homework. Doppler effect, which I didn't get to. Definitely useful, but just ran a little short on time. And then I think there's one problem on beats. So I'll post an announcement on the course webpage as to which problems will be need to be omitted from the homework.